All right, partial fractions, part two. All right, I'm gonna go through three examples. One I'm gonna look at three factors, one I'm gonna look at a repeated factor, and one I'm gonna look at what happens if you have a quadratic factor. All three of these are different than the first video. Again, if you haven't watched the first video I went through in general the partial fraction algorithm in terms of finding A and B, and then discuss kind of the reasons behind it. So I would suggest watching that. I'm going to go through these fairly quickly, assuming that you have a decent grasp on the general concept. So I'm going to take this, knowing I can't integrate it, and I'm going to rewrite it. And in this case, it ends up being that you have three factors. If you factor out an x here, you're going to be left with x squared minus 1, but then x squared minus 1 can be factored to x minus 1, x plus 1. So you can see how you have three factors here. So now I'm going to need a over x plus b over x minus 1 plus c over x plus 1. I'm going to need to solve for all three of those things, but the process is identical. Okay? The process is still, I'm going to multiply everything by the denominator and make this x squared plus x minus 2 equals, this is going to be a times x minus 1, x plus 1, b times x plus 1. Remember, the denominator of each one of these things is going to cancel. Oops. C times, oh, that's like the worst C ever. C x times x minus 1, okay? This is equivalent to that. And now I'm going to look at specific x values, okay? I'm going to start with an x value of 0. If x equals 0, what happens to everything? Okay, if x equals 0, this is negative 2. This is going to be 0 and 0, and it's going to make this negative a. Right? Negative 1, 1, a, negative a. Okay, that tells me that a has to equal 2. Okay, now I'm going to say, well, what happens if x equals 1? If x equals 1, this is 9, 10, 8, 0, 0, and then 2. So I get 2b, which tells me that b must equal 4. And then I think the most logical thing then is to use x equals negative 1, 9, 10, oh no, did I do that wrong? Yeah, I definitely did that wrong. 9, 8, 6. 6 equals, and then negative 1 is going to make that 0, that 0, and it's going to make this negative times a negative 2, which is then 2c, which is going to make c equals to 3. Okay, so we've established that a, b, and c have to be those numbers in order for this to equal this for all x. Again, I can pick any x value you want. You pick x equals 10, you're just going to get an equation that's got a number equals some a's, some b's, and your c's. I pick the easiest x values to eliminate variables so I don't have to solve a system. Again, but you can verify that these are the true values for all x. So I'm going to come up here and say, okay, I know that's 2, and I know that's 4, and I know that's 3. So instead of integrating that, I know I can just integrate those guys. So it's the integral of 2 over x plus 4 over x minus 1 plus 3 over x plus 1 dx. But those integrals are really easy. This is just 2 natural log x plus 4 natural log of x minus 1 plus 3 natural log of x plus 1 plus c. Okay? Again, 3 factors, not really that much harder than 2 factors. You just have a couple more things to do. It takes a little longer, but in general, it's the exact same process. Okay, so that's what you do if you had 3 factors. And again, if this was a cubic, well, you're going to get 3 factors. All right, let's look at the next one. The next one is a repeated factor. Like, what's a repeated factor? Well, this is going to be a cubic. If you multiply this out, this would be x cubed plus x squared. And you're going to have 3 factors here. And we can talk about why that causes a difference. But you really have x, x, and x plus 1. I mean, you can write them as that. But you're going to have to write it as a over x. And then you might be tempted to write b over x. But that doesn't make any sense. You got to think about that for a second. If you wrote a over x plus b over x, but couldn't you just add those together and get a plus b over x? And if a is a number and b is a number, wasn't a plus b just another number? So then really you don't have enough variables. This has to be x squared plus c over x plus 1. That's really the only difference of what happens if you have a repeated factor. Now this example is just like the previous example. You just got to figure out what all three of them are. Again, you have to kind of think this through. You can talk to me, you can look it up, but you can't have a over x plus b over x. It has to be b over x squared. You have to have the degrees of freedom, 3 degrees of freedom, to be able to get you these 3 coefficients. You have 3 things to control each one of those things. Okay, I'm gonna solve it the exact same way I solved all of these. I'm gonna multiply by the denominator on the left side, which is gonna clear out that denominator. Multiplying by this, well, it's gonna give me ax and an x plus 1. This is just gonna give me b times x plus 1, and then this is gonna be c and x squared. Again, x plus 1 canceled, leaving you the x squared. The x squared canceled, leaving you just the x plus 1. And one of the x's canceled, leaving you an x and an x plus 1. Then I'm going to say, all right, let's let x equal 0. Sounds easy enough. So if x is 0, then this is 3, this is 0, and this is 0, and this is just b. All right, that was cool. I know b is 3. Okay, I think then let's let x equal negative 1. If x is negative 1, this is 6 minus 5, so that's 1. I get 3, so that's 4. And it's going to make this go to 0, this go to 0, and all of a sudden I get negative 1 squared, which is 1, and I get c. Okay, now I know c is equal to 4. And then this last one, you know what, let's just pick x equals 1. We can't really get rid of everything, but x equals 1 is a nice thing to plug in. That's 6, 11, 14. And then here I'm going to get 1, 2, so 2a, 2b, right, I'm just plugging in 1 for x, plus c. 14 equals 2a, I don't know a, but I know b is 3, so that's really just a 6, and c is 4, so that's a 10, so that's 4 equals 2a, so now I know a is 2. And again, once you know all the numbers, a is 2, but b was 3, and c was 4, then you can take this integral and replace it by what you now know. That integral is 2 over x plus 3 over x squared plus 4 over x plus 1. Again, we rewrote the integral using partial fractions. Partial fractions does not do the integral for you. It just is the process that decomposes this into these, but these I can do. This integral, the integral of 2 over x, is 2 natural log x. This integral, that's not a logarithm, that's just power rule. Increase the power by 1 divided by the new power. That's just negative 3 over x. And then that's a logarithm for natural log of x plus 1 plus c. Again, repeated factor is very similar to just having 3 factors, except you have to make this adjustment. Okay, and I'm going to do one more. And I'm going to look at what happens if you have a quadratic factor. Now this is the worst one of the mix because, well, you have something that doesn't factor into something linear. See how that x squared plus 1 can't be factored, so you have some cubic thing? And here's how we have to deal with it. We have a over our first factor, and then we can't just do b over that quadratic factor. Again, we have 3 separate degrees of freedom. We need 3 variables. We need a, b, and c. But I can't just put b plus c in the numerator because b plus c, well, that's just another constant. I need these to be separate variables, b and c, that I can find. So I have bx plus c. I have some linear over some quadratic. And again, once you get this step, well, the rest of it is exactly the same. I'm still going to multiply by the denominator. 5x squared plus x plus 3 equals a times x squared plus 1 plus, I'm going to take this x and I'm going to multiply this in and get bx squared plus cx. And again, I'm just taking this and multiplying it in and getting this. All right, we can take a look now. So if x equals, oh, let's let x equal 0. That's probably the easiest one. 0, 0, 3. This is just a, and then this is 0, 0. So that means a is equal to 3. Okay? That was the easy one. The other ones are going to be a little harder because there's no value of x I can plug in here, no real number, that I can get rid of this x squared plus 1, so I'm not going to be able to get rid of x. So you're just going to have to look at two values. I'm going to go ahead and look at x equals 1. That gives me 5, 6, 9. 9 equals 2a plus b plus c. Now I do know a is 3, so that means this is a 6. So I'm going to move that over here and say that 3 equals b plus c. All right, so simplify that a little bit. Now I'm going to let x equals 2. If x is 2, this is 22, 25, 5a plus 4b plus 2c. Again, I'm plugging in 2 here. And I get this equation. Again, a is 3, so that's 15. 15 and 25 really just make 10. So I know 10 equals 4b plus 2c, and then I have to solve this system. Okay, this equation tells me that c is equal to 3 minus b. So 10 equals 4b plus 2 times. Again, I'm just making a substitution. Feel free to use elimination, whatever method you like. 4b plus 6 minus 2b. 6 and 10 make a 4. 4b and negative 2b make a 2b, which says I know that b must equal 2. But if b is equal to 2, c is going to equal 1. Okay, so that tells me that c equals 1. Now I can come back here. I knew a was 3, b was 2, and c was 1. Okay, so I can rewrite this integral as 3 over x plus 2x plus 1 over x squared plus 1. And we're getting close. You're like, well, I can do that integral. Okay, that's easy. Except, what about this one? Could I actually do this integral? And like, well, it's not really use substitution at first because it's x squared plus 1 over that. But what you do need to learn, and hopefully we did an example like this already in class, is that we can break this up. Okay, so I'm not going to do anything. I'm just going to algebraically split this fraction into 2x over x squared plus 1 plus 1 over x squared plus 1. And again, don't get lost in that algebra. That's not too bad. I just took this 2x plus 1 over this and wrote it as 2x over this plus 1 over that, right? I'm just separating the fractions. And now I can do these integrals. This is 3 natural log of x. This is a straight up use substitution. U is x squared plus 1, du is 2x, and so I just get the natural log of x squared plus 1. And then this tricky guy, 1 over x squared plus 1 is actually inverse tangent of x plus c. Again, this one's by far the hardest one. A quadratic factor ends up having to solve a system. And also, even when you decompose it, it still makes this integral a little tricky. But that's about as hard as they can get. Again, the 3 examples I showed what happens if you have three linear factors, a repeated factor, and now a quadratic factor. They're all just a little bit different, but again, the whole purpose of partial fractions is to take an integral that we cannot evaluate, algebraically rewrite it into something else, typically linear factors, but in this case a quadratic factor, and then we integrate the result. Again, these things are true for all x. You can take any x value you want, x equals 10, and this will be true as long as you solve for a, b, and c correctly. Okay?